Hi everybody, welcome back. We're starting at the very beginning of our Chapter 7 section on inclined planes and friction. And most of you were here for the first few slides of this, but I'm just going to go back to the beginning and recap. I'm going to kind of go over how we divide the components of weight force along an inclined plane. And then I'm going to skip example 7.1, because I think we did that in class. I'm going to go right to example 7.2, and that should wrap it up for this segment right here. So as you may recall, this deals with inclined planes, and whenever you have a weight or any kind of mass that is subject to gravity on an inclined plane, or I should say on any plane, the weight of it is always directed straight down. All right, mg, that's always true. Straight down, straight vertically. But the question is, how much of it is actually directed into the surface of the plane, or so directly into the face of it, and how much of it is being directed straight downhill. And I'll use green for that. So we call the downhill, or you might say the parallel to the plane force, we call that the force parallel, because of course it's like I said, it's parallel to the direction of the plane. We call this blue one here force perpendicular, and it's the weight force that is directed perpendicularly into the surface of that slope. And so if this were a flat surface, the weight force would be the same thing as the perpendicular force, right? But as this angle increases, less and less of it is directed into the plane, and more of it is directed downhill right here. So depending on what that angle is, that would determine how much of those forces is being applied and in which direction. And as you may recall, well, I'll go to the next slide. And son of a gun, I did it again. The parallel is, I like to make the parallel green. All right, force parallel green right here, and the force perpendicular blue. I have it backwards here on this one, so we'll make that one blue right there. So how do we find each of these forces? All right, well, with the parallel, it is the weight force times the sine of theta. All right, because theta is this right here, and since the weight force is vertical, it's really that same angle theta based off of the vertical. So this one here actually winds up being kind of down here, kind of like the opposite of the hypotenuse, and the blue one, the blue force perpendicular, winds up being adjacent to that same angle theta right there. So that winds up being mg cosine theta. Mg cosine theta. My drawing isn't very good today. Mg cosine theta. All right, and so I'm just going to write them out again. So force perpendicular equals mg cosine theta, and force parallel is going to be mg sine theta. Now, one other thing I want to point out to you is, okay, so we have this perpendicular force being directed into the face of the ramp right here, okay, perpendicularly into it. Well, the ramp has to supply some sort of force to support it as well, to keep the object from sinking into the ramp, and so we would call that, of course, the normal force, right? And the normal force is always perpendicular to the surface as well, just directed upwards. So in this case, the normal force N would always have to be equal to or equal but opposite to this force perpendicular right here, the mg. Well, I'll back up. Force perpendicular, which equals mg cosine theta. All right, so in most cases, when we talk about the normal force, that is the supporting force by this ramp right here, it's going to have to be the same thing, but just opposite, same thing, same magnitude as this perpendicular force being directed into the face of the slope right there. So let's see if we can do some examples. This example together in class, and we're not going to worry about that. We did talk about, I will say, the normal force that the toboggan exerts on the child, and that's very much like what we just talked about. But we're going to skip ahead to example 7.2, which deals with something that should look familiar to you, and that is a form of an Atwood machine. All right, now we actually have three scenarios right here, and what I'm going to do is I'm going to move on to the next page, and actually, no, I'm not. I'm going to do this. I should be able to. There we go. Hopefully we can get it all on one page right here. Hopefully you can still see that. If you have your notes in front of you, you should be able to read it anyway. But that way we can do it all on one page and still see the original problem right here. So we have an Atwood machine, and we have three different scenarios. We have right here, in fact, I'm going to move this over a little bit. I'm going to move over to that side. Right here, we have the system is in equilibrium. Okay, what does that mean? That means that the net force, oops, why am I drawing an E? It should be a sigma, right? The net force on the system equals 0, right? Because it's in equilibrium and there's no acceleration, therefore there's no net force. However, with part B and part C, there is going to be an acceleration. Right? You're finding the direction of the acceleration if the mass is this and if the mass is this right here for part B and part C. But for part A, we're going to say, part A, the net force is 0 newtons because the acceleration equals 0. All right, so that means all forces in all directions have to balance each other. Well, if we look at this system right here, we do have two forces acting against each other. First of all, we have this right here, the unknown mass mg that is pulling straight down right there. All right, that's the one end of the system. And if we follow the system up and over and bend it around corners like strings enable us to do, the other force pulling on this is what? Well, it's this 5.7 kilogram mass right here, but what part of its force is pulling against the string in that direction? It certainly does have a weight force straight down, and we'll call this mass 2 times gravity and mass 1 times gravity. All right, so this is mass 1 and mass 2. But really, is this weight force, is that acting along the length of the string? And the answer is no. It is pulling straight down, but what is acting along the length of the string? We would say it's the force parallel. That is truly what is acting along the length of the string and is balancing out this right here. So we should say that all these forces on either end have to add up to 0. So we said our net force is 0. Okay, so that's true regarding mass and acceleration. But it's also true, like we always say, oops, I'm going to make that black, that the net force is the sum of all the components acting on the system right there. And so we have this component end force, mass 2 times gravity, ultimately acting against the parallel component of this weight force right here. So I'm going to just write it like this. In fact, I'll even color code it so you can see. First of all, we need to determine what we want to decide to be positive or negative. Because after all, you got these two forces acting against each other, right? The point here is that it doesn't matter, but one has to be positive, one has to be negative. I'm going to say that this direction clockwise is positive, and that direction right there is negative. All right, so that means that our force parallel is going to be acting negatively, and our mass 2 times gravity is going to be acting positively. All right, so we need to write it out like that. Let's color code it like I said I would. So what are our component forces acting against each other? Mass 2 times gravity, which, by the way, we want to find out what mass 2 is if this system is going to be in equilibrium. All right, minus what? Minus the force parallel, right? The parallel force, you might say the parallel to the surface component of this weight force right here. And so if we expand that out, and you'll excuse me if I don't keep using color codings, that takes up more time. I'm just going to stay with black here. That winds up being mass 2 times gravity minus what? How do we state the force parallel? Well, that's mass 1 gravity times sine of theta, right? And by the way, we have our theta. It's in here. I covered it up a little bit, but I believe that's 35 degrees. Okay. So that is our way of stating the component forces. This weight right here is acting against the parallel weight of this mass right there. All right, and what is all that equal to? Well, it equals the net force on the whole system, which we said before is going to be 0 because it's in equilibrium. All right, so we can say this. Mass, do I have that right? Yep. Mass to, still not writing, there we go. That was kind of weird. Sorry about that. I'm going to erase this. I'm going to rewrite that back in. Mass 1 gravity sine theta. Sorry, my pen wasn't working there. All right, so all that's going to be equal to 0, so let's write it all out. Mass 2 times gravity minus mass 1 gravity, and we do know what mass 1 is, right? Sine of theta equals 0 newtons. All right, well, that's going to be easy, so let's solve for our mass 2 times gravity. For our mass 2. Mass 2 gravity equals m1 g sine theta. What can we do right here? Well, we can certainly solve for mass 2, but one way to make it easier for us is to cancel out our g's, right, because they're on both sides. And so we can say that mass 2 has to equal, in order for the system to be in equilibrium, mass 2 has to be equal to mass 1 sine theta. All right, mass 1 is 5.7 kilograms times the sine of 35. I get 3.27. I'll just say 3.3 kilograms. That's got to be our mass for this object right here that is balancing out the parallel force of this right here. Okay? All right, let's put this into quadrants right here. So that was part A. We'll go a little bit faster on part B and part C. Part B, the system acceleration. Can I even write here? There we go. It wasn't working. The system acceleration is going to be, we want to find the system acceleration. Sorry. Acceleration of the system equals, we don't know. All right. Well, the mass 2 equals 3 kilograms, and mass 1 is still, what is it, 5.7, right? 5.7 kilograms. And we want to find out what the acceleration of the system is. So is it going to be accelerating positively? And by the way, we're calling this direction still positive. Or is it going to be accelerating negatively? Well, I would say, take a look at this. This is less of a mass than is required for it to be in equilibrium. So I'm guessing that it's going to be accelerating negatively in the negative direction. But that's ours to find out. Okay? So what's one thing we can say about the system? Well, the net force on the system equals the mass of the system, so that's got to be both masses added together, times acceleration of the system, which is what we're solving for. It's also true that the net force as components is going to be equal to mass 2 times gravity minus mass 1 gravity sine theta. Okay? So we can say that m2g minus m1g sine theta equals mass of the system, big M, cis if you want to say that, times acceleration of the system. So therefore, the acceleration of the system is going to be mass 2 times gravity minus mass 1 gravity sine theta divided by big M, mass of the system. Okay, now I've just about run out of space right here. And you know what? I'm going to cheat. I'm going to steal from this side right here. Nope, I guess I can't do that. Sorry about that. Okay, I'm just going to, let's see, I need to steal some more space somewhere. You know what? I'm going to do this. How about that, huh? There we go. I could do that. All right, so acceleration of the system equals a mass 2 times gravity, so that's 3 kilograms times 9.81 meters per second squared, right? Minus, what's the mass of the big one? 5.7 kilograms times 9.81 meters per second squared times the cosine of 35 degrees, all over what? The mass of the system. So that's 3 kilograms plus 5.7 kilograms. And that should give us our acceleration for the whole system. So, 3, I'm just calculating it out right now. Let's see, 5.781 divided by 8.7, I'm going to say. Sorry about that. Aha, okay, so we have a negative 0.31 meters per second squared. Just like we predicted, right? It's a negative acceleration. It's not very much, but it is definitely negative because this mass right here, mass 2, and this one is less than is required for equilibrium, so it's gonna start to go that way in the negative direction. All right, part C, and then we'll be done. Part C, I know it looks like an E, doesn't it? C, mass 1 equals 4.2 kilograms. Okay, let's predict what's going to happen right here. 4.2 is less than the mass of the smaller mass that require. I'm sorry, is more than the mass of the smaller mass required for equilibrium. So my guess is that it's going to accelerate positively. All right, I'm going to jump right to, where is it? I outline it in yellow right here. This right here. This is essentially the exact same problem as part B. The only difference is we've got a different mass for mass 2. So I'm going to immediately jump right to this statement right here because this is a component statement for net force and a system statement for net force set equal to each other. All right, so we're going to go right here. So M2 gravity minus mass 1 gravity sine theta equals mass of the system times acceleration of the system. All right, and like we said before, the acceleration of the system is going to be mass 2 gravity minus mass 1 gravity sine theta all over big M. So what's that equal out to? All right, this is going to be what's our mass in part C? 4.2 kilograms, right? 4.2 kilograms times 9.81 minus our old 5.7 kilograms, 9.81 times the cosine of 35. Got it in there, okay? All over what? All over the whole system mass, right? So that's going to be over 4.2 plus 5.7 kilograms. And sorry for not putting my units in right there. I just kind of ran out of space. So what is our acceleration going to be? 4.2 minus 5.7. Oops, sorry. 5. I'm talking this out loud without really even doing anything in front of you, aren't I? Cosine of 35. 1 divided by, what's that? 4.2 plus 5.7, so that's what, 9.9, right? Over 9.9 kilograms. I get 0.92 meters per second squared. And just like we predicted, it's a positive acceleration. Why? Because the forces are now in the positive direction's favor. It's going to be moving that way because this mass 2 right here is greater than before. So, 3 different ways of doing this problem. Well, it's 3 different problems, really. Okay, we've got equilibrium, we have this end winning out, and then we have this end winning out right here, all producing different accelerations. So, I hope that helps. We're going to be getting into actually calculating the value of the friction force when we get back into class. So, in the meantime, please let me know if you have any questions, and I'll be glad to get back to you as soon as I can. Thanks for watching. I'll see you on the next one.